And so integration by substitution is a method of reversing the chain rule. And when we did the chain rule, I don't know if you remember. Let's write out our chain rule again. So if you have f of g of x, what is our chain rule? Our chain rule says do the derivative of the outside function, keep the inside function the same, right? Multiplied by the derivative of the inside function. And on your formula sheet, here we'll pull it out, how does the chain rule show up on your formula sheet? Don't know if they have this form or the U and the V form. Yes, they have, on your formula sheet, they have this form, dy dx equals dy du times du dx, which says that you first have to make a substitution. So if I had this function, something simple with a more complicated chain rule. So I'm going to start off with my original function being 3x squared plus 7x to the 5. By now, you're quite good at the derivative, and you just do it directly. 3x squared plus 7x, keep the inside the same, subtract 1 from the exponent, multiply by the derivative of the inside. No problem. Okay? And for the most part, we're using this kind of notation when we're thinking. Right? Derivative of your outside function, keep the inside the same, multiply by the derivative of the inside function. Generally, we don't use this notation. How did we, if we wanted to use that notation, I don't know if you remember, but when I taught the chain rule, I showed it once, and I said this method sucks. And then we just didn't do it again. But the method that sucked helps us with integration. So we're going to review the method that sucked a little bit. The method that sucked a little bit said, change the inside function to u equals 3x squared plus 7x. Then your original function becomes y equals u to the 5. Can you see that? And if I wanted to, with u, I could find the derivative of this easily, that du dx, right, that's the derivative of this function, would be 6x plus 7. And this is easy. I could find dy du would just be 5u to the 4. And if I put all of that information into the formula of the chain rule, I would get that dy dx is equal to dy du, 5u to the 4, multiplied by du dx, 6x plus 7, and then I'd have to substitute back dy dx equals 5. Instead of u, I could write 3x squared plus 7x to the 4 times 6x plus 7. Can you see why we said this method sucked for the derivative? Because now that you've done lots of chain rules, you can just go to the answer directly instead of having to do an extra 15 lines of work. Okay? However, when you're integrating, integration isn't always as easy just to see, oh, a chain rule happened and I see all the parts and I put it back. And sometimes in integration, the function has been simplified a little bit, so even trying to work it backwards, even if you can see it, runs into problems with coefficients and fractions. Okay? So here were some of the ones that work out easily. And this was a question that was in your notes from before. If you have to work backwards, can you see a chain rule happened? Right? The key is noticing the derivative of the inside function is multiplied afterwards. And this one is so perfect, right? I can just go 3x squared plus 5x to the 5. And then I don't have to do anything else plus c. Because it was so nice. Everything worked out perfectly. Now, it's not going to always be the case that everything works out perfectly. And so for integration by substitution, what we're going to do as a method is we're going to say, if I notice a derivative of something else is present in the question, and it doesn't have to be a perfect derivative, but a mostly perfect derivative. So like the derivative of x squared plus x will be something plus a number. Coefficients will be there. This one worked out perfectly, but not always. But if I notice that I have a function here and its derivative is here, then integration by substitution, what we'll do is we'll say, let u equal the inside function, 3x squared plus 5x. Then du dx is going to be 6x plus 5. And we can say, and although technically you're not just multiplying by dx, for simplicity's sake, we're multiplying by dx. 6x plus 5 dx. See what I did there with just move the dx that was on the bottom? Now, the dx on the bottom isn't a number. And usually in mathematics, you cannot just multiply part of a function to the other side or divide part of a function to the other side. Like if you have sine x, you can't just like divide both sides by s to get rid of the s in the front. And then you have in x. That doesn't work. So technically this shouldn't work, but in this situation, and you can look up a long-winded explanation online if you want, it does. Okay? So we'll just accept it and be happy. So what does that mean? It means when I am integrating this function, which is 3x squared plus 5x to the 4, 6x plus 5 dx. That means if I do this kind of substitution, I'm going to have, instead of this, I could write u. And instead of all of this with the dx, I can write du. And now I've changed my integral to something that's super easy. How do you integrate u to the 4? Add 1 to the exponent, divide by your exponent plus c. And if I substituted back now, the 5s would cancel out. Which is the same answer we got right away because we noticed it was easy. Okay? But we're going to find out that even though we did not use this method when doing the chain rule, because we didn't need to because we could do it easier, we will find that when we work backwards, this is really, really helpful. Yeah. So when we have a chain rule that's happened, what we have to look for in an integral to tell us, ooh, this is going to be best done by integration by substitution, is when you see a function inside of another function, and its derivative present in the same integral. So I'm going to highlight all of the functions in yellow. Can you notice that's not yellow? Can you notice that that x squared minus 7 is inside the power of 4? So we have an original function inside of another function, and its derivative is present. In the second one here, I see the natural log is inside the power of 4, and the derivative of natural log is present. Okay? Can you see that we could have had this same question with the x in the denominator? And the derivative would be present, but a little bit more hidden. And that's what makes integration by substitution sometimes hard to see, because sometimes the derivative is hidden. In the next one, I like the power rule ones because they're really the easiest ones to see. That you can see that that x squared minus 3x is inside a power of 1/3. And its derivative is right here. Okay, derivative of sine is cos, derivative of cos is negative sine. In this one, though, what function is inside of another function? Exactly. Sine of x is inside e to the x, and the derivative of sine x is present. Okay? Here, this one is not easy to see a function inside at all. In fact, you could argue that maybe there isn't anything inside here. We've just got something in the denominator, something in the numerator. Okay? But I notice when I look at both of those functions that if this is the original function, this is the derivative. And so that might help me later on recognize what I need to do with the integral. Okay? When working through these, can you see power rule here? Right? Can you see power rule here? Power rule here. Can you see e to the x rules here? Okay? What rule do you see here? The natural log. See? Exactly. That's the perfect look. That's the perfect look. Like, what? I don't see no natural logs. Right? Yeah. What are you talking about? Right? You can't see the natural log very easily there. Right? That's why the only couple people said natural log and most of people went, what? But when we do the substitution, you'll see the natural log. Okay? We'll get to that one. Here, this one's a little bit easier. What's the inside function? This one right here, right? And where's its derivative? Right there. Do we see an inside function and its derivative in the next one? Yes. Inside function is tan. Its derivative, secant squared. This one is missing dx at the end. Whew. And this one is going to be fun and interesting afterwards. What's the derivative of sine? What's the derivative of cos? So in this one, we could have possibly thought this is the inside function and this is its derivative. Or you could argue that this is the inside function and this is its derivative. Whoa. So that one's going to be a little bit messed up that way, because you could do it in two different ways and get two completely different answers that are completely right. Ooh. Right? Which goes totally against your experience, because usually when you get a completely different answer than me, I mark it wrong. So this is what substitution looks like. If we have a chain rule, okay? In other words, when we have, and I'll highlight here because this is easier to see what we've been doing, when we have an inside function and its derivative present. And I'm going to highlight the gx with the derivative. What we do is we let u equal g of x, which replaces this with just u, and then the derivative g prime x gets replaced by du. And the purpose of substitution is to change a complicated looking integral into something easy. And then integrating the easy thing and substituting back in the end and going, oh, I can see the answer now, but maybe I couldn't see it originally. So we're going to do each of these with the chain rule. Okay? And you might look at it and say, ooh, I think I could do this directly. But every time a little bit more detail gets added, you're going to find that using substitution just takes away some of that complication. Okay? So here, if we go back to our highlighter and keep highlighting the same way, there's our inside function. There's the derivative of our inside function. So in substitution, we always let u equal that inside function. And if you've recognized the right inside function and recognized the right derivative, things will work out nicely. So then the derivative of this, du dx, would be 2x. And instead of writing d over du, I'll do it in 2 steps right now, but eventually you'll just do this. Right? Du dx would be 2x. If I move that dx to the other side through some magical mathematics, then du is 2x dx. And our integral with the substitution, now instead of 2x, x squared minus 7 to the 4, I just have u to the 4. And instead of 2x dx, I can just write du. So we've changed from integrating with respect to x to integrating with respect to u. This is a really easy integral. How do we integrate a simple power? Add 1 to the exponent and divide, plus c. And so substituting back, yes. For this question, because this question said using substitution, you would have to show the substitution work. You couldn't just write the answer. But this might be one where you would still say, I can see what the answer would be. Okay? Now, the reason why you're going to start to like substitution is even though you could see what the answer is, sometimes you're going to get mixed up with like, oh, I forgot to divide by 5. Or you're going to forget small little details as you go through because you're trying to do it all at once in your head. So here, keep our highlighting colors. Here's our inside function. That's the derivative. So if off to the side I say let u equal the natural log of x then du would be 1 over x dx. And so I'm going to get u to the 4 and then du. Exactly the same integral as before. Yes. If we're going to substitute it back in, what we have to make sure is that this has to match up perfectly in order to substitute, and it won't always. Okay? We're starting off with the easy ones where everything matches up, but we're going to get to a point where they don't match up perfectly, and then we'll have to deal with that. Okay, I'll get you to try. The next couple still match up perfectly. Substitution-wise, let u equal x squared minus 3x, so du will be 2x minus 3 dx. Substitute that in, and you just have u to the 3rd, add 1 to the exponent and divide. Substitute back in. Good to go. Yes? All right, next one. Inside function, let u equal sine of x. Derivative, du is equal to cos x dx. Substitute in, and we change our integral to something easy. What's the integral of e to the u? E to the u. Substitute back. So this was the one where people were like, what? Natural log? What? And there's not really a function inside. But we do find that we have, using our highlighter here, we have an original function and we have its derivative. So just by the fact that you see an original function and you see its derivative in the same question says maybe substitution's going to work. So if I let u equal that bottom function, then du would equal 3x squared minus 5 dx. Now substituting that u is on the bottom of my fraction, the whole top and the dx gets replaced by a du. What would I have left on the top of my fraction then? Just a 1, I guess. And now when it's written this way, you're like, oh yeah, the derivative of natural log is 1 over x. Derivative of natural log of x is 1 over x. And so if I am integrating and I have a 1 over u, then the integral is going to be the natural log of u. Substituting back, I'm going to have the natural log of x cubed minus 5x plus c. And I think this is the first really good example where your brain might not have said, I can see that right away and just integrate directly. That using substitution was really helpful in this situation for me to see it. Pretty easy substitution in this case. This just becomes cos u du. The other thing that I really like about substitution is it lets you focus on less details at one time. So now I can just focus on, is the integral of cos going to be negative sine or positive sine? Because that's the one that always gets your brain going. Positive sine. So then I can just go, okay, it's positive sine. I don't have to worry about all the other data. And now I can substitute back. Now, some of you might like the challenge of trying to do it directly and seeing, can I hold all of that information in my head to figure it out? But over time, you're going to appreciate the simplicity of using substitution, that it can let you focus on other parts of the question. Okay, I really want to get to I. No, I want, yes. Oh, we're only on G. Okay, I'll do G quickly. I'll do H mostly quickly, and then we can get to I. So G, the inside function, really easy to see here that it's tan of x. Derivative of tan is secant squared of x. Oh, and this is the one where the dx is missing, so add that in, please. And here we can think, is it going to be positive cos or negative cos? Negative cos. Plus C. Perfect. So sometimes substitution is really straightforward. Most of these examples up to G, I would call them really straightforward. Even the natural log one was a really straightforward one. This one's a little bit unconventional, okay, because the derivative of sine is cos, and the derivative of cos is negative sine. So technically, we could use either one as u. But since the derivative of sine is positive cos, it's going to make more sense initially to let u equal sine 2x. Now, this one, actually, H and I, the first time something interesting happens. What's the derivative of sine 2x? It's cos 2x, but there would be a chain rule, right? Times 2. And so I've got a problem, because if I get du by itself, I'm going to just put this 2 in front, okay? I can't just replace this. I can't just replace that with du, because du has an extra 2 there. How can we get rid of that 2? Divide du by 2. Right? If I divide both sides of this by 2, are you okay if I write 1/2 instead of dividing by 2? Then I get cos 2x dx by itself. And now when I substitute back in, well, sine 2x, that's going to be u. And cos 2x dx, that's going to be 1/2 du, which is really, if I rearrange this, the same as 1/2 u du. Okay? And so integrating this is easy. Add 1 to the exponent, divide, plus c. And so I'm going to get 1/4 sine squared 2x plus c. And if we have time at the end of class, we're going to get really messed up on this one, okay? Yes, you could put this in brackets and put the squared outside is fine. Okay? All right. So hopefully we have, what do we got? How many more examples till we're done? IJ and example 4. So not too many. We might be able to get really messed up on this one at the end. Have some fun with it. Okay? That is a right answer. Perfect. But we're going to get creative with this one. Another one where things don't really match up. But can you see that the 4x squared plus 1 is inside the function? What's the derivative of 4x squared plus 1? 8x. Do we have an 8x? No, but we have an x. And 8x and x are both the same kind of function. They're both lines. So we're going to be able to do a substitution here. But if you try to do this one in your head, whoa, the numbers are going to get just mess you up. So we'll start by letting u equal that inside function. And then du dx is going to be 8x. Okay, maybe I'll just write the dx on this side right away. But I don't have an 8x. What do I have? I have just an x. So if I want just an x dx, I'm going to have to divide both sides by 1/8. Oh, I'm sorry. Divide both sides by 8. Multiply both sides by 1/8. Thank you. So that means that this x dx is going to get replaced by that. So now when I go to integrate this, what am I going to have? I'm going to still have e. Instead of 4x squared plus 1, I'm going to have u. Instead of the x dx, I'm going to have 1/8 du. Integrating this, 1/8 e to the u plus c. Substituting back, 1/8 e to the 4x squared plus 1 plus c. Funny that they wouldn't go into class. I guess because every other day you don't. They're nervous that you, since you came late for announcements 2 days ago.
No, I was in French last time.
No, you were writing a math test last time.
That wasn't my turn to do.
Okay. All right, no fighting. Okay, easy. So we're starting to see in these examples where things don't match up perfectly. Okay, again, you're going to look for your inside function. Can you see that the 5 minus 2x to the 4 is inside a square root? And can you see that the derivative of that would be negative 8x cubed? We don't have a negative 8x cubed, but we do have an x cubed. So we're starting to see that that coefficient doesn't matter. It's just to make sure that we have the right variables. Because now if I let u equal 5 minus 2x to the 4, then du will equal negative 8x cubed dx. And all I have in my equation is an x cubed dx, so I'll have to multiply by both sides by negative 1/8. So I substitute in. Instead of writing the square root of 5 minus 2x to the 4 on the bottom, are you okay if I write that right away as u to the negative half? Or is that too many steps at once? Okay. Move it down. Is it all right if I change the square root to a half right away? And then this will be negative 1/8 du. So I replace the x cubed in the dx with the negative 1/8 du. And I have 1 over u, and the square root I wrote as a half. Then that u to the negative 1/2 could come up using my negative exponent rule, and I would still have negative 1/8 du afterwards. How do we integrate u to the negative 1/2? Add 1 to the exponent. Divide by our new exponent, plus c. Substitute back. This is going to be negative 1/4. U was 5 minus 2x to the 4 to the 1/2 plus c. I think this is a great example of where if you think you can do them in your head directly, this is really hard to see that there would have been a negative 1/4 out in front. Again, whenever you would want to check to see if you've done this right, you can do the derivative of your answer to see if it matches up. Right? If I did the derivative here, I'm going to get a negative 1/8 out in front. This is going to stay the same. Subtract 1 from the exponent will give me a negative 1/2, which will put that on the bottom. Chain rule would also multiply by a negative 8x cubed, and that negative 1/8 and the negative 8 would go away, just leaving me with an x cubed on top. And so now we can combine the last question, example 4. We can combine the rules of substitution and what we did the other week on solving for c to find the actual equation. So the derivative is 8x over 4x squared plus 1. We want to find f of x. So f of x will equal the integral of 8x over 4x squared plus 1 dx. Because if we have the derivative and we want to find the original function, we have to work backwards, which is integrating. Here, I'm going to let u equal 4x squared plus 1, because then du is 8x, and everything matches up perfectly. So nice of them. I guess so nice of me. At this point, substituting in, I'm going to have the integral of 1 over u du, which is going to be the natural log of u plus c. Which, if I substitute back in, is the natural log of 4x squared plus 1 plus c. We're not done yet. We have to find c. Okay? So this is, we know that f of x equals this, and we also have a point. The point that we have is that it goes through 0, 4. In other words, when I plug in 0, y is going to be 4. So natural log of 0 plus 1 is natural log of 1 plus c. Mental math, what is the natural log of 1? 0. And so we find out that c is equal to 4. So we can say f of x is equal to the natural log of 4x squared plus 1 plus 4. First time we did this question, we let u equal sine 2x, and we got this as an answer. Question is, what would happen if we let u equal cos 2x? Then du, right, the derivative of cos is negative sine. We would still have the chain rule where we'd have to multiply by 2 dx. And so if I wanted to just get sine 2x dx, I'd have to multiply both sides by a negative 1/2. And then my integral would become u times negative 1/2 du. Integrating this would still be u squared over 2, the negative 1/2 out in front, plus c. So we get negative 1/4 cos squared 2x plus c. Compare that to our first answer. It's different. Now we have a cos instead of a sine, and now it's negative instead of positive.
Change it all to like substitute like cos squared and 2x.
Well, you could use an identity, right? You know that cos squared of 2x is equal to 1 minus sine squared of 2x, and simplify that. And it'll be different because you'll have a number, but that number gets absorbed by the c, and it's fine. Okay, but now, question, would you agree that this is equal to what did I do? I used an identity. What do I know? Okay, I'll do a step in between here. I'm going to write 1/2 times 2 sine 2x cos 2x dx. What's 1/2 times 2? Nothing. It's 1. Did I change anything? No. But that allowed me to go, hey, wait a minute. When I have 2 sine x cos x, that's an identity that it's equal to sine 2x. So if I have 2 sine 2x cos 2x, that's an identity that's sine 4x. And this is an even easier integral where you don't have to use substitution. When you integrate to sine, is it going to be positive or negative cos? Negative. So I'm going to get negative 1/2 cos 4x. But I would have a chain rule where I multiply by 4, so I also have to divide by 4 plus c. So we get negative 1/8 cos 4x plus c. C is an element of the reals. Another totally different answer than the other ones. But they're all the same. They're all right, not the same. Different answers that are right. So in that sense, if you're looking at getting them right, they all work.
Well, like if you move all of them back, would it still equal?
If you took the derivative of all of them, they'd still be the same.